Good afternoon, everyone. It's my great pleasure to introduce Fiona Burnell. Fiona got her PhD from Princeton University and was a postdoctoral fellow. I was in All Souls at All Souls College in Oxford before joining University of Minnesota as a faculty member. Fiona is one of the leading young theorists in condensed matter physics, and her work has reflected a great beauty and depth and breadth across a variety of topics, from ranging from field theories and mathematical aspects of topological phases to exotic fracton phases of matter, and more recently to more quantum information theoretic works on quantum games and dynamics and quantum stars. And we're very happy to have her here today to tell us about these many phases of condensed matter that's reflected in her work.
Thanks. So thanks for coming. It's a great time of year to come here from Minnesota, as you can imagine. Basically I want to tell you a little bit about some of the foundational tools that we use to understand phases of matter, namely symmetry and topology. So I wanted to start by framing the question, and I imagine, for many of you this is not unfamiliar, but in condensed matter theory, we study systems with many particles, and we're typically interested in regimes where, interactions are quite strong, okay? So basically, calculations are very hard, and you can't build things from the bottom up, okay? And in particular, often like perturbative quantum field theory from the kind of single particle approach is not always an effective tool, okay? But at the same time, the potential payoff for understanding these kinds of systems with lots of particles and strong interactions is really big, right? So if you think about the technologies that have changed the world in my lifetime and your lifetime, dating back to the semiconductor revolution that led to this laptop and now your phone and all of these kind of progress in hard drive technology through to superconductivity, which allows us, among other things, to build really powerful magnets and study collider physics if anyone's into that. Right up to the modern era when people are starting to think about actually building or trying to build experiments that go towards being legitimate quantum computers. So all of these are advances that have required us to understand systems of many interacting particles, often in a regime where quantum mechanics is a fundamental part of the game, okay? So it's a hard problem, but there are many compelling reasons to study it. But because it's a hard problem, we need qualitatively, different tools than you do coming from a few particle perspective. Okay, and one of the foundational tools that we understand to think about these systems are familiar from everyday life, which is the observation that if you look at a typical material, maybe you're looking at water, okay, that it can have dramatically different behavior depending on the conditions. So actually, I don't think I have a pointer. Do I have a pointer? Maybe I don't. But anyway, on the left-hand side, in the blue region, is where we live in Minnesota for much of the year, okay? In the region where water is solid, okay? And, over in the green region, well, that's California right now. I've never been to California when it's green, but it is green now. And that's where water is liquid. And the point is that, these different regimes have very dramatically different long-range properties, okay? And so, maybe if you want to just understand these qualitative differences, you can zoom out a little bit. And what you find when you do that, okay, and the other observation, right, is that, so, the water looks very different from the ice, clearly, I can walk on ice, I cannot walk on water. But at the same time, there's a very large range of temperatures and pressures where, things are liquid or things are ice. And so they kind of all look the same. And so this, first kind of insight is that when we study these complicated many-body systems, you don't need to study every single system, right? We can kind of arrange them into these different phases of matter. And all you really need to know is how to understand one point in the blue phase and one point in the green phase, and then you're pretty close. Okay, and so for the field theoretically inclined, you can say we need to sort of find an RG fixed point in the phase and understand that. Okay, so this is kind of the foundation upon which we build our understanding of quantum materials. And in the framework of understanding phases of matter, two of the most powerful tools that we have are to think about symmetry and topology. And I think the idea that symmetry is a very powerful tool in trying to do hard calculations in physics is familiar to all of you. So, like for the students in the audience, right, you take QFT and like, maybe you do some really long calculation and you work really hard and you find like 0, right? Why is it 0? Well, if it's actually 0, typically there is some fundamental reason that it's 0, and that's because there's some symmetry, okay? So understanding these symmetries can save us from having to do a lot of work, even in regimes where we can hope to calculate things, and in regimes where maybe we don't know how to calculate things, it still allows us to make some pretty deep qualitative statements. Okay, good. And so to kind of set the stage, let me give you just kind of an overview of the ways in which symmetry and topology shape our understanding of condensed matter physics before talking about some slightly more specific examples. So, if you go back to just understanding the kind of materials that you encounter in your everyday life, like water, and you ask, how does symmetry tell us about, the difference between water and ice? The answer is, it tells us about the difference between water and ice because of, what the symmetry is, okay, right? So, if you look at if you look at water, right? You take a puddle of, a little vial of water, right? And you kind of rotate your perspective on those water molecules. It doesn't really matter, what direction you're looking at. It doesn't matter kind of which piece of the sample you're looking at. Everything kind of looks the same, okay? So like under translations and rotations, everything looks the same. Clearly that's not the case for ice. We have this regular structure, right? And so, it's not invariant under rotations. And also if I translate by, and here I don't have a pointer, but you can see that if you translate by some small amount, okay, that's not a lattice constant, but you don't get back to the same place, okay? And as somebody once put it to me, if you're a pragmatic person and your goal is to understand the kinds of things that nature gives you, then this is really where you stop, because like 99.9% of the systems that we encounter in nature kind of have this underlying them. Okay, but there are some other ways, some qualitatively different ways in which symmetry can tell us that different systems are different. And that is, that you can have the same symmetry, okay? But that symmetry can, give you something unusual, typically at the boundary of the system. And so I think, here at Stanford, the idea of topological insulators clearly need no introduction because of the, seminal contributions that were made by, among others, Shucheng Zhang and Xiaolong Qi when they, here. So, but, the basic idea is that I can have a system with surface states, and in the case of topological insulators, one of their defining properties is that they conduct electricity, okay? And that property is really very robust, even if you add, a lot of disorder and other things to your system, okay? And I'll tell you, kind of the underlying reasons for this in a minute. And the other ingredient, right? So you notice this word topological insulators, okay? And the other ingredient that comes into our understanding of phases is topology, okay? So, for example, here's an example that, maybe I don't have like some, conducting surface states. Maybe I do, maybe I don't. But maybe it's the case that I have a few just bulk states that are very low in energy that all have the same energy. So a kind of degenerate ground state space, right? And maybe that degeneracy is there not because of some coincidence, right? So when things are 0 or almost 0, generically, then it's not a coincidence, but they're there because there's sort of something that winds in the system, okay? And that can wind in different ways. And this is what we call topological order. Okay. And so what I'd like to do in this talk is tell you a little bit about, some of my favorite examples of how, sort of symmetry and topology talk to each other to allow us to understand different kinds of phases of matter. And the two themes that are going to run through this talk are the relationship between, symmetries in condensed matter systems, anomalies, which, you might encounter kind of in a more field theoretic context, and this kind of something interesting happening at the boundary. And the second theme, as we explore that, is that we will, here we go, okay, is that, we will encounter a kind of interesting interplay between symmetry and topology, and the idea that sort of topological defects are a kind of, fundamental part of this picture and a fundamental way of thinking about and understanding new ways to have phases of matter. Okay, great. So let me begin with this word anomaly. Probably those of you who have seen anomalies at some point, you typically first encounter them in the context of, relativistic quantum field theory, where they've been discussed for a long time. What you learn is that you start with Lagrangian, okay, so some theory that classically has a symmetry. But then when you try to do the quantum mechanics of that theory, right, you find that symmetry is broken in some mysterious way by these, very high energy virtual particles, okay? So it's this kind of like mysterious process from the very ultraviolet. And that sounds really exciting. And, in condensed matter, there's like a very boring picture of this, which is completely not exciting, which is, okay, so this particular anomaly, these are called triangle diagrams, okay, it's called the axial anomaly, and let me give you the condensed matter picture of what's happening here, okay? So here's a one-dimensional system of fermions, and I have some fermions, so this is a plot of their energy versus their momentum, okay, and when the slope is positive over here, that means that these fermions are right moving. When the slope is negative over here, they're left moving, okay? And the observation is that, if I just have these fermions here, and in particular there's no like background electric field, okay, that the number of right movers and left movers are separately conserved, okay? It's quite a natural thing to write down. But if you turn on a chemical potential, that's like kind of tilting, okay? It's like tilting this surface of the Fermi sea, okay, relative to your momentum states. And so, what happens is this electric field, like, changes the momentum of the electrons, okay? And so like in this picture, we have this very obvious, statement that you lose some left movers and they become right movers, okay? And this is, a very pedestrian picture of how to think about this, deep and mysterious anomaly. Okay. And so, this picture seems a little bit disappointing, but there is one crucial observation, which is that, it was important in my picture. So it wasn't so important that I had the right movers over here and the left movers over here, okay? I could have, sort of drawn the same conclusion if these had crossed, say, in the middle, okay? But it was pretty important that I had only right and left movers, right? Because in particular, a natural consequence of this argument is if you only have right moving particles, right, and then you turn on an electric field, that, charge is not conserved, okay? And so, depending on whether how fundamental you view charge conservation, in particular whether you want to gauge it or not, you might view this as acceptable or not. But in condensed matter, right, this has a very, I think, beautiful like physical manifestation. So you can ask, look, this conservation of right versus left, well, maybe we're not so interested in this, but this conservation of charge we're very interested in. And so, where could you have this system that has this anomaly? It looks like it's not possible if I want charge to be conserved, okay? And the answer is that these appear, right? And this is like something that, nature gave us when people started taking two-dimensional electron gases and sticking them in magnetic fields, that these anomalous systems appear naturally, very typically, at the boundary of higher dimensional bulks, okay? And so the kind of starting point that we start from in condensed matter when we talk about anomalies is, what is an anomaly? An anomaly is basically a realization of a symmetry, or some kind of symmetry that is not consistent as a symmetry only of a d-dimensional theory, but that we can make consistent as a symmetry of a d-dimensional theory on the surface of a d plus one dimensional bulk, right? So this picture here so over here, this is a quantum spin Hall, this is a topological insulator, but let's focus on the left, okay? This is a picture of just a, kind of two-dimensional system of electrons in a very high magnetic field, right? And at the boundary of this system is this actually chiral one-dimensional fermion. It transports charge, and it's associated with a quantized conductance, which is a very clear transport signature of these systems. And this, as I just told you, is something that is not compatible with charge conservation in one dimension. And what lives in the bulk of this system is something which has, it has what we call a non-zero Chern number, or if you wanted to kind of write down an effective electromagnetic response theory, it would be a Chern-Simons theory. Okay, I don't want to give you any details, but this is also a theory that has, does not conserve charge in the presence of a boundary, okay? And so what's going on here is, what we call anomaly inflow, which is the idea that, neither the boundary nor the bulk conserve charge by themselves, but when you put them together, then everything is fine, okay? And for this reason, you can't have one without the other, right? And this is why these boundary states are so robust, right? Because basically they're required by the bulk in order to be consistent with the symmetry. Okay. All right, so that's kind of the basic perspective on, anomalies in condensed matter physics. And now I want to, kind of talk through a few examples that I think are interesting simply because from a condensed matter physics perspective, it's very natural to think about symmetries and consequently, the ways that these anomalies might happen or these surface states might happen in the context of theories that are not natural to look at if you're, studying sort of relativistic quantum field theories and from a more high energy perspective. And so I'm going to talk about two qualitatively different examples of how, we get some new kinds of anomalies and new interesting boundary states that are quite different from, what you would get by starting with, say, a perturbative quantum field theory. And these come from like two different things that you can do. So the first thing you can do is to access something that you couldn't get by thinking about, perturbations about a single electron picture, is you can go and start with a system that is intrinsically strongly interacting, right? Meaning that I can't, describe it well with a picture of individual electrons at all, okay? And so that'll be the first example. And the second thing that you can do is you can change the nature of the symmetry. Okay, and the particular way in which I'm going to talk about that is that, I'm going to introduce a symmetry which is like intrinsically not relativistically invariant, that has some kind of underlying like geometrical structure that you can think of as knowing about a lattice. Okay, good. All right. So another thing, which I'm sure I don't need to introduce here, is, these strongly interacting phases that we cannot access by thinking about, single particles. So where on earth would you find this? Well, of course, as I'm sure you all know, you find it in the fractional quantum Hall effect, okay? So this is what Bob Laughlin won the Nobel Prize for. And the basic idea here is that in the presence of strong interactions, right, you can get phenomena that emerge which you simply cannot understand by thinking about a single particle picture. Okay? In the case of the quantum Hall effect, these particles, which kind of in the simplest incarnation are known as Laughlin quasi-particles, are things that you should think of as carrying both an electric charge and a magnetic flux. Okay. But what's unusual about them? Why can't we even understand them by starting to think about the electrons, which are the microscopic constituents of this system? Well, there are in fact two reasons for this. And these reasons kind of talk to each other in an interesting way. Okay. So the first interesting property of these particles is that you'll notice that I wrote a little E/3 here, okay, which is to say that Laughlin showed that they carry a fractional electric charge. And this fractional charge is very different from, like the charge of 1/3 or 2/3 that you get when you look at quarks, because microscopically, right, so a quark is like a little, fundamental particle, but here, microscopically, if you zoom in and you look at the system closely, you will see only electrons, okay? There's no E/3 anywhere when you look closely enough, but only when you step back and you look at kind of, the low energy physics of this system, do you see that in fact there are objects that you should think about as particles and they carry a fractional electric charge, okay? Clearly not something you can get by, starting from electrons and trying to kind of build things out. So this is an emergent phenomenon. At the same time, the other property, which is fundamentally different from electrons, is that these guys also have a statistical interaction. They're what we call anyons, which is like different from fermions and bosons. So here's a picture of two of these particles, right? And I'm going to take this guy around the other guy, okay? So that's like exchanging them twice, topologically, okay? In space, that's equivalent. And, so if I did this for fermions, right, I would get 2 minuses, which would be a plus. If I did it for bosons, I would obviously also get a plus. And if you do this for these E/3 Laughlin quasiparticles, you get a phase factor of like 2π/3, okay? So they have fractional charge and they have fractional statistics. All right, and you might ask yourself, oh, sorry, this is why you should never put animations in your talk. You might ask yourself, why would you think, can you have one without the other? Is there any, are these related in any way, okay? And the answer is that, in principle you can, but in the systems that we are given in nature, things like the fractional quantum Hall effect or, quantum spin liquids, which is another example that there's good experimental evidence of now, it seems like these two phenomena come together, okay? So fractional charge and fractional statistics. And why is that? Well, it didn't have to be so, but both are things that, are possible when you have these quasiparticles that are emergent, okay? Good. And so, so then you might start to ask, well, okay, like, what about this fractional charge? Like, is any fractional charge okay? What can I do? How can I assign the charges of some symmetry to some particles that have some statistics? And this is kind of a general mathematical question. And you could ask in particular whether any of these symmetries are anomalous, and if they are anomalous, what are they the boundary theory of, okay? So let me start by making what, a kind of obvious observation when you think about emergence and how it works, which is that there's some basic rules of the game that you just can't violate, okay? Which mean that the possible fractional charges that you can give to your particles depend on their statistics, okay? And the basic idea here is very simple. So if, again, I have my E/3 quasiparticles, okay? But if I put 3 of them together, then I have something that's like an electron, okay? And an electron is not an emergent particle, so the electron shouldn't, see anything funky, okay? So if, and so in particular, the electron, so 3 of these statistically are an electron, okay? And they should also have an integer charge because the electron has integer charge. So, what charges am I allowed to assign these guys if their statistics have this factor of 1/3 in them? Well, a charge of 1/3 is fine. A charge of 2/3 would also be fine, but a charge of 1/2 is not. Okay, so it's kind of a basic observation. Good. Oh, sorry. There's the animation. Okay, so that's kind of the rule that we play by. And now, let's ask, okay, so given that we have some symmetry charges, you can ask like, are all of these symmetries consistent, okay? And the answer is no. And in order to, so, I'm not going to go into the details, but let me say a little bit about the kind of fundamental mechanism, okay? So one way it turns out that you can detect anomalies is that you can talk about kind of adding background gauge fields. And one way to think about that is to add what we call symmetry fluxes, or topological defects in the symmetry, okay? So here's a very sort of beautiful picture of, that you should have in your mind when you hear symmetry flux or symmetry defect, right? So this is like a parking ramp kind of defect, right? And it has this feature that if you go kind of all the way around in space, you go up by one row, right? And so, you've kind of gone around this special point and you've been translated, okay? And so let me kind of take that picture and make it a little more concrete. So this is a general feature that, when you have a symmetry and you start to introduce sort of topological defects in your symmetry, that they have this property that as you go around them, the symmetry kind of acts in some way. So here's a more concrete illustration. Here is, here's a lattice, and this lattice has translational symmetry in the x and y directions, okay? But, over here I've introduced a defect, and the defect is I've just like stuck in another row of atoms here, okay? And great, so now we're gonna go around this defect, and we're gonna go around the defect in the following ways. So first we're gonna go down by 3 sites. Then I'm gonna move to the right by, I believe, 4 sites, okay? Now I'm gonna go back up again by 3 sites, and I'm gonna go to the left, right? Okay, and if I did this anywhere on the lattice that did not enclose this point, clearly I would come back to the same place. I've just gone, down, right, up, back. But when I go around this symmetry defect, something has happened, and what has happened is I have been translated by one lattice site. Okay, and so this is a kind of basic picture of a general phenomenon that you introduce these defects, and these defects, kind of act on the particles as they go around them, carry out this symmetry action. Okay, good. And so now there's a picture here that sort of gives a bunch of technical information, but the basic gist of how you can understand what kinds of fractional charge can you assign to these emergent particles that maybe have this interesting fractional statistics basically goes like this. Let's suppose that we introduce some symmetry fluxes into our system, okay? And we can infer, quite a bit about what happens to these symmetry fluxes when you, sort of combine them together in different ways, right? So this is sort of, when I bring 2 symmetry fluxes together, maybe this, I have a G, right? And I have an H. And so here, this thing down here should be like a GH symmetry, okay? And you can start asking, so you can understand that certain things that have to be true about the way that these symmetry fluxes combine to give actions of, products of 2 symmetry elements that are, there's restrictions placed on that from the way that they act on the particles, okay? And what this picture is showing is that there are some consistency conditions that, that these sort of different ways of combining the symmetry have to satisfy. And what you find is that if you choose the wrong kind of symmetry action with these assignments of charges on your emergent particles, that this data is inconsistent, okay? And so this is what we call a 't Hooft anomaly. It means that, if we try to add these fluxes and make a consistent theory, that basically things break down. Okay. And so as I said, in condensed matter, the, natural interpretation of this is, boy, this, is not something that naturally happens in 2 dimensions alone, but it could be something that happens at an interesting boundary of a higher dimensional system, okay? And indeed, that is the case for these kinds of symmetries, okay? So you can show that once you add this funny symmetry to the boundary of a higher dimensional system, you have a sort of a version of this anomaly inflow such that the bulk cancels the boundary anomaly. And the way that it does that, if you actually, so these loops are kind of symmetry defect loops in 3 dimensions, okay? So you go around the loop in 3 dimensions and the symmetry acts. And the way that the bulk cancels the boundary anomaly is kind of interesting, which is that these loops actually have a kind of non-trivial braiding when they encircle a base loop, okay? So So if you just have a loop through a loop, you can't get anything interesting, but if you have a loop through a loop and a base loop, you can get this kind of interesting non-trivial statistics, and that is the part of the bulk that cancels this boundary anomaly. Okay, good. So maybe let me kind of give you what I think is the takeaway of this first example. So the basic idea is, I have these exotic emergent particles, and maybe it's natural to think of them as having these, emergent fractional symmetry numbers, okay? The symmetry charges. And this leads to, new kinds of anomalies that are intrinsically, features of these strongly interacting systems. And that, these interesting anomalies kind of naturally lead you to these interesting bulk three-dimensional models, which, again, if you kind of think of what's going on with these symmetry fluxes, have these interesting statistical properties. Good. Okay. So the second class of examples that I want to talk about, so that was kind of, option one, was to look at symmetries acting in these very strongly interacting systems. And there's other, kind of variants of this that you can think about. But the second, kind of qualitative thing that I can do is I could change the symmetry, okay? And the way that, or an interesting way to change the symmetry is to make it into a symmetry that cares about the underlying geometry in a way that, familiar global symmetries do not. And so the two things that I'm going to touch on are dipole moment conservation, okay, so a symmetry in which not just a total charge, but in fact a total dipole moment is conserved, and something that we call subsystem symmetry, which is basically a stronger version of this, but where I would say we understand more. Okay, so let me start with dipole symmetry and tell you a little bit about why these symmetries are different and why you might be interested in them. And I should preface this by saying that actually a lot of people are interested in systems with dipole symmetry right now because several experimental groups have started to work with systems that have, a kind of approximate dipole conservation by sort of taking one-dimensional lattices and tilting them, okay? So maybe that's one reason. But the other reason is simply that the dipole symmetry talks to geometry in an interesting way. So what is dipole symmetry? When would you get it? Well, basically you get it in systems where a particle can't move by itself, but you have these correlated hopping things, right? And so that's exactly what happens in these tilted lattices, that, if you move a particle by itself, suddenly it has a very different energy, right? So that's very far off resonance. But if you move them together, this one goes up and this one goes down, and so that's not suppressed. And so when you only have this correlated hopping, not only the total charge, but in fact, at least naively, the total dipole moment is conserved. Okay. And so why is this, interesting, again, apart from experimental motivations? Well, one reason you might be interested in this is that dipole conservation is qualitatively different from charge conservation because it talks to the spatial symmetries of the system. So in particular, in one dimension, it talks to translation symmetry, and this is, quite obvious because when you translate this dipole charge, it shifts by the total charge of the system, okay? Okay. Now, you might ask, what does that interplay with geometry get you? And I think, there are several hints that it can get you, quite a bit of stuff that's maybe quite different. So, one example, and these are not systems with exact dipole symmetry, but if you take just a system of, weakly interacting fermions, and you sort of have a low energy effective theory with dipole moment conservation, we can go from systems that have conducting surface states, as was the case for a topological insulator, to systems that have conducting states only along, say, the edges separating two faces on the boundary, or even maybe they just have, sort of a little spin a half degree of freedom at each corner, Okay, these are called higher order symmetry protected topological phases, and in some, qualitative sense, they're kind of dipolar-like cousins of topological insulators. Another thing that you can have, and this has been known for a long time, is sort of an exact ground state degeneracy when you have sort of dipole and translation symmetry. And actually it turns out that you can generalize these to cases where you can show that there's kind of phases that have not a ground state degeneracy, but sort of symmetry protected gaplessness, so symmetry protected low energy modes. Okay. So there's quite a lot of hints, I think with dipolar symmetry, that there are things there that do not occur when you have, say, just a global charge conservation law. Okay. And so to explore these possibilities, one thing that actually turns out to be convenient to do, if you will, is to think about not just dipole conservation, but a stronger version of that, which is what we call subsystem symmetry. Okay. And subsystem symmetry is something that's cropped up in a variety of contexts. And the basic idea is that rather than having a symmetry that acts on a conservation law for the system as a whole, I'm going to have conservation laws, individual conservation laws on different lines. Okay. Now, what is the relationship between this and dipole conservation? Well, one obvious consequence is if the charge is conserved on each line, that particles cannot be individually mobile, right? But of course, if I take a particle and its antiparticle partner, these guys can move. Okay, so dipoles are mobile, but only perpendicular to their dipole moment. Okay. And so these are, again, how is this different? Well, first of all, there's a specific choice of these subsystems. In this case, they're lines, right? But they could be planes, they can be fractals, okay? But there's something that, qualitatively, I no longer have rotation invariance. I've chosen a symmetry group that just breaks that rotation, okay? The current conservation laws are different, okay? And again, for the field theoretically inclined, this is connected to the fact that gauge fields have different mass dimensions. So everything works a little bit differently here. And you might ask, why would you ever think of such a strong, restrictive symmetry condition when you're thinking about real phases of matter? And one of the reasons that we started thinking about them is that they are connected to what we call fracton orders, which is actually a new variant of topological order in 3D, okay? And so there is this close connection. It's a kind of interesting analog where we have statistics, okay, and point particles, but instead of having point particles that can move in any way, we have point particles with restricted mobility, and so we can get these kind of emergent statistics in these three-dimensional systems. And so one of the interesting things that we get out of subsystem symmetry is some picture of what kinds of statistics we can have in these systems. Okay, and so so let's talk a little bit about, so what I'm going to do is just maybe give a qualitative sketch of what kinds of boundary states, what kinds of protected boundaries you can get in models with subsystem symmetry. And the basic idea is that exactly the same as I mentioned kind of at the beginning with this anomaly inflow, that you can look at, given your symmetry, what kinds of bulk theories can we have, what kinds of boundary theories can we have, and how can those cancel each other out? Okay. And so let me just list a few examples. So the first example is if you have time reversal invariance and a subsystem symmetry, you can find a model that has, kind of a trivial, trivial boundaries here, okay, but something protected at the corner. So a leftover sort of free spin 1/2, and therefore on a square, a system like this has a protected ground state degeneracy. okay? A second example is what we call the two-dimensional cluster state, okay? And so in this system, I have actually, you know, two different kinds of subsystem symmetries. So blue lines and red lines, and they have different kinds of charges, okay? And it turns out that when you have subsystem symmetry, you can have, you know, you can stabilize a boundary that actually has a zero energy state for every site along the edge, okay? And so that's what this little blue thing means. And there's a slightly different zero energy state at each corner, okay? And, okay, this is, you might think that this is a little bit like having rows of one-dimensional systems with, you know, just kind of stacked together with interesting things on their boundaries. But in fact, that's not the case. So you can show that this is an intrinsically two-dimensional property of the system. And the reason for that is that you can actually, you know, kind of add any one-dimensional stuff that you want to this, and there's still going to be something left over of this protected boundary stuff, okay? Good. And, you know, a final sort of example to put in the kind of toolbox of things that we can do with these phases are a version of this kind of axial anomaly, okay? So you can also have a system where, with a surface state that you can think of as either having sort of right-moving dipoles and left-moving dipoles, okay, or up-moving dipoles and down-moving dipoles, okay, such that, you know, when you apply a certain background field, the numbers of left movers and right movers are not separately conserved, okay? And when you put this on an appropriate bulk, you can sort of, you know, cancel this anomaly and get an interesting gapless boundary state. Okay, good. So, you know, that's just a few examples of the different kinds of things that we can do. So we can, you know, write down models that have different kinds of weird boundaries, and the boundaries can be weird all along the edges. They can be weird at the corners. You know, we can have sort of stuff in you know, two-dimensional boundaries and one-dimensional boundaries and so on. Okay. Now, okay. And the interesting, you know, feature that's very different from what you get in, say, topological insulators is that, you know, for all of these boundaries, states that we get, they have some kind of dependence on the underlying geometry, okay? So either they appear at corners, right, so a kind of sharp corner, or maybe the number of, you know, sort of low energy degrees of freedom that I have grows with the size of the boundary, okay? They always have this geometrical dependence. And that's kind of, so that, you know, leads you to ask the question, well, what if I throw away this, you know, rather pathological subsystem symmetry? You know, can I get anything interesting left? And the answer in many cases is that you can. So if you, instead of requiring charge to be conserved along each line, if you simply require charge conservation and you start from a state like this, but you also preserve crystalline symmetries, you can get to a related phase, which is indeed a strongly interacting variant of these higher order topological insulators with something at the corners. Okay. Now, a second way, so one sort of feature that comes out of the intricate dependence between the symmetry and the lattice geometry here is that these give us hints about what kinds of phases of matter we might have when we have, you know, maybe just crystalline symmetries that are different from what we get in just ordinary global symmetries. Okay, so it kind of spits those out as one interesting corollary. A second context in which we find analogs and much more kind of pedestrian systems of these anomalous subsystem symmetries are when you start thinking about not just conservation of charge, but conservation of momentum, okay? And so in particular, I wanted to talk about this kind of, this sort of subsystem version of the axial anomaly, which has a very nice analog in systems of free fermions. So you can think about a two-dimensional fermionic system, okay, which has sort of left-moving fermions at negative kx and right-moving fermions at positive kx, okay? And it turns out that if you look at kind of the way that, and so here what happens is if I apply an electric field is not the charge is not conserved, but rather that the momentum is not conserved, okay? And this gives me a response that actually is very similar to this axial subsystem symmetric anomaly. And so you could think that these kinds of studying these subsystem symmetric things might give us some insight about the way that things like conserved quantities like momentum or other geometrical conserved quantities can talk to global symmetries in a non-trivial way. Good. Okay. So let me end there, and just to kind of recap. So symmetry and topology are kind of very powerful tools in understanding phases of matter, right? And on the one hand, understanding these anomalies gives us an insight both into interesting new kind of field theories, interesting phases of matter, interesting surface states, and what kinds of interesting bulks they might live on. And that there are these class of symmetries which seem highly exotic, that are very much not relativistically invariant, and they have an underlying geometry, but that these seem to give us access to some interesting phenomena that maybe have close cousins in more realistic material systems, and so are worth exploring further. So let me end there, and happy to take any questions.
So that last example you gave, is that a saddle, or were you sitting at the saddle point or away from the saddle point here?
Oh yeah, sorry. So the blue is like below the Fermi sea, and the red is like above. Yeah, and so the thing that I should say is, you could think about this as a hypothetical thing. It's an open 2D Fermi surface. So the difference between if you have like just this subsystem symmetric model, you can have a gapped bulk, and you can have this kind of pattern of dipolar flow on the boundary, which is very similar to this momentum flow, okay? In the free fermionic system, this is the surface of like a vial semimetal with a kind of quadrupolar vial cone structure.
What is the thing that's anomalous?
Yeah, that's right. So what happens here, if you just look at this state, okay, what happens here is that, I have, let's say I apply an electric field, right? And so I have, so the point is that the right movers are over here and the left movers are over here, okay? And so I have equal numbers of right movers and left movers, so charge is conserved. But when I apply this electric field, right, momentum is not conserved, because I'm going to be moving, like changing left movers to right movers, and therefore I'm going to be moving states at, minus k to plus k. So like these are like, sorry, I should say this is, right movers in y, left movers in y. So I'm applying an electric field in the y direction, and the momentum in x is going to change, which is, yeah, so that's the kind of qualitative difference. And yeah.
So So when you were making this connection between crystalline symmetries and subsystem symmetries, so is there a route to realizing fractonic physics with these crystalline symmetries without these like tilted fields and the stuff that people have been doing in cold atoms? Or?
That is a very good question. I haven't. I don't think so, because for a fractonic system, the restricted mobility is very fundamental. So I think one of why does this work? Why can we get something that has the same boundary physics without the subsystem symmetry? It's because those, so those states are states that, they only really needed this, they only really needed the subsystem symmetry so they couldn't kind of hybridize with each other, okay? So in other words, the role of the subsystem symmetry was to pin them at the corners. And that you can do with a crystalline symmetry. Whereas, all of the things that we love about fracton order is point particles in 3 dimensions that have some kind of non-trivial statistics, that's what's exotic. That really requires subdimensional mobility, and so, there, if you take, kind of the symmetry analog of that is that, you do really need these separate conservation laws in different planes in that case. Yeah.
Any other questions? Okay, well, let's thank you.